Hello everyone and welcome to Handmade Hero, show that we code a complete game live on stream, and part of that complete means that lighting is in the mix. Unfortunately, one of the hardest things to do in 3D graphics, or just in graphics in general, is lighting, but we are working on it right now, and we're hoping to have that wrapped up in the next few weeks, although it is going to take a while. I say a few weeks, I probably mean the next 6 or 7 weeks, right? But we're doing the best we can here. It's a difficult problem, not the kind of one you want to solve on a stream that's 2-hour chunks, but we have to do everything here, so we're doing it. Before I get started today, I just want to mention 2 things. One, we do have a Discord now. There's a button down on the page here, or if you're using this watch page on the schedule, there's a button here. You can jump to the Discord, and the Discord will hook you up with other folks in the Handmade Hero viewing audience, as well as myself. I spend a lot of time on there now. I put the little Discord app on my phone, and every time I'm sitting around with nothing to do, waiting for something, I'll just pop it open. So I moderate it, and I participate in the discussions there. So come say hi. It's been pretty great so far. And while we're on that subject, although this won't make much sense to people watching these after the fact, like if we can wave some kind of a good luck charm for our friends over in Japan. We got a lot of people who participate at the Discord and also, watch the series in Japan right now. They are in the middle of a pretty nasty typhoon. I believe it's called a hurricane in the U.S. on the East Coast, called a typhoon in Japan, but basically the same thing. Very, very heavy windstorm with a lot of rain and flooding. And I'm told that interior Tokyo is faring pretty well because they have a flood control system there, which is pretty awesome actually. But the more outlying areas are getting hit pretty hard. So hopefully everyone's okay. And I guess we'll be checking the Discord later today and tomorrow to see how everyone fared. But hopefully everyone's okay. So if you get a second, point a good luck wand their way and hope everyone comes out of that okay. I know we got at least I think 2 people over there who are active participants oftentimes, but I'm sure we also probably have a bunch we don't hear from very often who are over there. So best of luck, everyone, and hopefully it all works out okay. Now, the other order of business is after this stream, we will be rolling into another John and Casey gaming extravaganza. John and I were going to play some more multiplayer games today. Some of you caught us playing Satisfactory a couple weeks ago. John wanted to play through 2 games, John picked out 2 games that maybe we'd try. Unrailed was one of them. We Were Here Together, I think, is the name of the other one. And they may not be good, so we don't know. Maybe we won't really be playing them, but we're at least going to give it a shot. So after this stream, stay tuned. John and I will be squatting up. I believe we will be streaming it. He usually likes to stream gaming sessions, so I'm assuming unless he says today is the one day he doesn't want to stream it, we will presumably be streaming that. So stay tuned for that as well. On my channel or on twitch.tv/naysayer88 is the other channel. And I think the squad thing lets you swap between them really easily, so chances are you can just stay tuned on this channel and you can then switch over to his channel at any time. I think that's what's supposed to happen with the new Twitch feature. I've never actually seen it myself, but we do turn it on. All right, moving on. What we were doing last week, and we need to basically finish up or at least come up with our first draft this week, is we were looking at the way in which... Oops, that's not what I wanted. We were looking at the way in which we might go about getting lighting into our pixel shader, or as it's called in OpenGL, a fragment shader. And this is kind of it's a difficult question. And the reason it's a difficult question is because it's very much experimental for me. I don't do GPU programming really as my focus. And unlike some things, some aspects of coding, the difference between a generalist and a specialist is not particularly large. So, a a generalist is going to do basically the same thing as a specialist, modulo a little bit of improvement maybe the specialist makes or something. Some areas are like that. GPU programming isn't like that. So in GPU programming, the difference between what a specialist can do and what a generalist can do is actually quite large. So the difference in quality in a lighting solution I'm going to do is going to be pretty dramatic probably between the difference in quality that a specialist do. So somebody, for example, who's a graphics researcher at NVIDIA is probably going to be able to design a much better lighting algorithm for Handmade Hero, were they to do that, than I'm going to be able to do. And again, that's because GPU technology moves quickly. It's something that gets revised year over year over year over year. And so a generalist such as myself, who does all of the things in a game engine oftentimes, has not had enough experience with whatever the current target platform is to really have a strong point of view on what works well and what doesn't, right? So although I do keep fairly up to date on what's possible, meaning I understand the kinds of things GPUs can do and how they're doing them, because that's important and not that hard to keep up with. For something like designing a really difficult algorithm like lighting, what you're talking about is really a very precise, very finicky area of the code that really only someone who knows exactly what is possible and how it works on a broad range of hardware platforms that are relevant to that day, right? That's really the only person who can do an exemplary job. And so for us, this is going to be a bit of a struggle because we're flying somewhat blind there. The generalist is flying somewhat blind. They just know, here's a bunch of features that the graphics card has that I could access. I don't know how performant each one of them really will be. I can make some guesses. I might be wrong. There could be pitfalls hiding there that I don't know about. And again, that's because if you're just not up to date enough on it. So what I would probably do normally in most circumstances, if I was doing this myself, we would go read a bunch of research papers on this topic, and we'd probably pick based on a lot more input, right? We don't do that on Handmade Hero, and the reason we don't do that on Handmade Hero is because I want to show the process of muddling through things sometimes. It's important, because there won't always be someone who's tackled the problem that you're thinking about, or not tackling it in the way that you need it tackled, and so you do need to learn to do these things. So it's important to approach problems, even like this one, and see, how would I solve it if I just had to, right? It's good practice, and you should do it too. But it's worth knowing, and it's worth understanding, that in a professional setting, you would also, in addition to practice, you would also want to understand the fact that reading a bunch of papers about this and or consulting with some experts in GPU programming would be valuable and probably will help you develop an algorithm better than the one you can develop yourself, because if you're not a GPU specialist, you just don't have the experience with the actual practical implications of the things that you're using. So it's worth getting that out of the way just so everyone has perspective on it. But that said, we are going to do it ourselves. And the reason for that, like I said, is because it's important to learn how to do that, because sometimes you do have to go somewhere that other people haven't gone. And that's just part of programming, part of being a strong engine programmer, is not being afraid of tackling a problem that doesn't have an easily published solution that fits your needs, right? So, where we left off was in the fragment shader, like I said. Excuse me. A little bit stuffy today. Where we left off was in the fragment shader. And what's going on in the fragment shader is we need to reconstitute inbound lighting using some kind of a spatial query. We don't know what it is or what it will be. We need to reconstitute our inbound lighting so that we can light a pixel that has never had any lighting computed on it. This is the idea behind light probes. They're saying, look, it's too expensive to compute the lighting every pixel. We could never do that with the horsepower we have available at the time. But what we can do is compute the lighting at various sparsely populated points throughout the world. And when we go to light a pixel, we'll look at where those sparse points are, and we'll reconstitute our lighting by interpolating between the lighting we solve for at those sparse points. That's all a light probe really is, right? The rest of the complexity of a light probe is in the details, in how you implement it. There's really nothing else about it. There's nothing else complicated about it, right? The concept is very, very simple. Lighting is expensive, compute it in as few places as possible, and try to reconstitute the lighting per pixel by looking at those sample points, right? So, for us, that means each pixel, we need some way of finding out which of these light probes we want to sample from. And the problem that we have is it would be very, very straightforward and probably preferable, right, if we could just pick the closest light probe and light the pixels as if they were lit by that probe, by the lighting that's at that probe location, right? That would be the best possible case for us. And the reason that would be the best possible case is because that would be like one voxel lookup that would give us back an index, and then we would just look up the lighting probe inbound light representation using that index, and we'd be done, right? So that's by far the preferable method, and we could implement that fairly simply. It would be one texel fetch that fetched into the voxel, and then some number of additional texel fetches depending on how much lighting data we wanted to extract. If we wanted to extract 6 separate pieces of lighting information, one for each direction out of the faces of our light probe cube, for example, that would be 6 more fetches. Or if we bundled multiple directions into one somehow, maybe it's less. But, you know, it would basically be a total of 1 texel fetch to look up the light probe index and 6 texel fetches to look up the lighting contribution. And that's a total of 7 texel fetches, and we're done. Not particularly complicated. And then we would just go about applying whatever equations we wanted to estimate the inbound light based on that probe. So we then get to sort of an obvious simplification, which is that if we are assessing what the lighting information would be at a particular direction, well, 3 of the faces of the cube in a lighting, so if you look at how much inbound light there is in a cube that we're tracking, there's 6 faces of the cube. And the inbound light coming through each of those 6 faces has certain limitations as to how it could light a particular object. If you assume no translucency and no subsurface scattering sorts of operations, which we are not considering because we don't really have any way to take advantage of that with our sprites, we don't need it, right? Maybe there's some times that we would, but they'd be a special shader, presumably. So if you're just talking about reflective light, then a particular pixel that we're trying to light has a normal pointing in a particular direction, which means that all of the incident light has to be pointing into, basically, or the direction of sampling has to be pointing in the same direction, let's say, as that normal. That means that at any given time, 3 of the faces of our cube will be contributing to lighting, and 3 of the faces won't be. So in addition to that one piece of information we have about, look, we would look up a particular light probe, and then we would fetch its information, we can probably cut that down to 3 texel fetches, only those necessary to fetch the 3 faces of the cube that will actually contribute, because we know the other 3 faces, unless we're in some really weird, like, oh, we're trying to light smoke or something, right? Where you're trying to get back-facing light coming through as well. Except in special purpose shaders, we really only need 3. So that would get us down to just 4 texel fetches for the lighting. And so that would be really nice. That would be great. But the problem there is, what do you do at the edges? At some point when you move something around the environment, or you just imagine just a flat plane and we're lighting each pixel, at some point you cross over to where the closest light probe is actually different. And so when we look up into the voxel which light probe we should light with, there's going to be a pixel who says it's this light probe over here, light probe A, and then a pixel right next to it will say, oh, the closest light probe is light probe B, right? And if we haven't done any blending, then those 2 pixels will get lit completely differently, right? And this creates a huge problem for us. We'll have all of these hard edges in our lighting and it will look really bad. Or maybe if you're, into weird artwork, you could just lean into that aesthetic and say, well, okay, I'm just going to do it that way and that's the way the game looks, right? That's a totally fine decision to make, not one we're going to make. We want to figure out a way to do the blending. And the problem we have with the blending is that it's a three-dimensional world. So any pixel could be related to any other pixel by being a little bit above, a little bit below, a little bit left, right, back, forward. And so really what we have is effectively a cube-based blend. There are 8 lighting probes near to this pixel. One that's to the, one that's the closest in this direction, one that's close that direction, this direction, right? And so as you move continuously through this space, if we want the lighting to be continuous, we need what is effectively a trilinear blend. We need to blend 8 incoming sample points together so that we're smooth no matter how we move through the space. And the lighting never has a hard seam. That's what creates a nasty problem for us. So you can see here where we have our lighting information. This, for example, is what it looks like to do texel fetches on 8 different things, right? You can see me texel fetching each of these lights, and I would need to know the index for the light in each of these 3 different places. I would then lerp them together, right? And you can see me doing some of that, like getting the lighting data here, right? And this is if we're only doing one side. So you can see it's like 16 texel fetches, really nasty, only to do one face of the cube. This will multiply itself out, right? I would end up with 3 copies of this. We're just drowning in texel fetches, right? It's not great. And so one thing that was proposed at the end of the last stream, and that I think is an interesting idea and probably one we should explore, because there are some ways we can make this work, is what if instead of doing this manually, where we actually track light indices themselves, what if instead of doing that, we actually just had a voxel representation of the lighting itself, and we just went hog wild and said, look, we've got 6 faces of this cube. We're saying we're tracking the lighting through those 6 faces, right? That's what we're going to do. Or something else. Maybe we switch to spherical harmonics, so we sort them in a slightly different way. I don't know, right? But we're going to do something where we have some number of terms stored for lighting into a voxel, and we're going to fetch them. If we were to store the actual lighting terms into the voxel, then what we can do is instead of calling texel fetch here, we can just, instead of 8 calls to texel fetch, we can make 1 call to texture. And that will do a trilinear blend on the voxel for us, right? Now, it's still doing a full trilinear blend on the voxel, so we haven't really saved a lot of math. But what we have done is given the graphics card the opportunity to heavily optimize that fetch, because it knows we're doing a trilinear blend from a 3D texture, which is an operation native to GPUs, right? So it can probably run it a lot more quickly. There's a lot less bookkeeping. It needs to do a lot less work because it already has specialized circuitry most of the time designed specifically to fetch texels in a way that blends them together. So it's not going to be super confused about what we're doing and have to do each step manually. It's going to have a bunch of those steps fused together, and it's going to do stuff like pull out bundles of pixels, blend them together directly, and do like the whole thing in 1 or 2 steps that we were having to do in 16 steps, right? And although that savings may not sound like a huge amount of savings because, hey, there's not that much code here, when you think about the fact that this is code that has to execute on every pixel of our screen for our display, right? That's just a lot of work, right? Anything we can do to make this simpler for the graphics card is huge. So it does seem like that may be a better starting architecture, because if we could do it that way, maybe we can avoid some of this bookkeeping that could slow the GPU down, make it difficult for it to hit 60 frames a second doing this kind of advanced per pixel work, because again, it's just the less you throw at the GPU per pixel, the better. So let's think about what that would look like, right? You can see here us operating on our voxel. We're producing our voxel location, and you can see us doing stuff like flooring, right? And we're computing these pieces of information. And what I think we want to do there is say, all right, so let's just pretend that we don't want to do that anymore. What would it look like? Well, one of the nice things is even this information goes away, because now that's part of the texture lookup itself. So if we were to assume that we had some number of these 3D textures and they were representing our actual lighting, then what we would say is, you know what we really have here is the different sides of the cube. And so we would have something more like this, right? We would have, well, I guess we want to just do our box surface, I don't know what we want to call it, our box surface ordinals here. So it'd just be like west, east, south, north, down, up, right? So we would feed in 6 separate samplers, one each for the directions of our lighting. And that would actually be what we sample. So then here we would pull from those lights that lighting information. And again, probably just going to be a V4 sample here. We're going to be looking up in a U32 texture that will then kind of come out to the sampler. What we want to do here is say, all right, let's get the light from the west, right? And that's going to be a texture lookup. And that's going to be from our light sampler west. And we're just going to use our Vox. You can see here, right? We have our relative P, that maps into the voxel. We have our Vox index P, that makes it into our UVW. What I'm going to call that instead is our voxel UVW now, because it's really, that's what it is, like a texture lookup. Now that's what we're treating it as. Same value, it's just making it clear what we're going to do with it. We're not going to convert it to indices into the voxel. We're going to let the graphics card take it as a UVW, and it's going to do that mapping, right? So what we want to do now is say, well, really the value that we want here is not where it is in the cell. What we want is where it is in the texture. So instead, we're just going to do inverse voxel total dimension. So we're really just taking how big is this voxel at all, and we're gonna make that be the value that we actually want. So we don't want to map it into cells so that we have which cell and how far in the cell. Instead, we want to just say, and you know, I guess we didn't actually put these out here. Yeah, it doesn't looks like we didn't really put these out here. So these again have to be up here as things that come in as parameters that we specify, because the shader itself has no idea where this voxel is supposed to be, right? It doesn't know any of that information. So we need to tell it. We need to have the voxel min corner. That's actually V3, right? Because it's where it is in space. And then we have the total inverse total dim, or maybe I should call it voxel inverse total dim, right? And that, again, that's just a scaling value that says, well, we need to, you know, account for how large the voxel is, so shrink or scale the input values to conform to the voxel. So there's 0 when you're at the min edge and 1 when you're at the far edge, even though the voxel itself may be 300 meters long or something, right? So that's all we really needed to do there to produce a voxel UVW for our lookup. And then what we need to do is do a 3D texture fetch, which I never remember the names of any of the things in OpenGL. Let's load that up. I should just pin that. How do you do that again? You don't like this, right? Yeah. So really what we want to do now is just do a texture fetch, right? And you can see here, here's the actual information for how textures are fetched. You can see that you've got samplers here, and the samplers for texture can be anything, right? So I can pass it a 1D texture or a 2D texture, which, like we have been doing, or I can just sample from a 3D texture. And all I really need to do is just pass it the appropriate p-value, which again has to be 0 to 1 from the beginning and to the end of the texture on each dimension. That's exactly what I prepared here. So this call doesn't, it's exactly the same as looking up at any other texture. we're just saying it's a 3D texture now. So instead of doing a 2D placement in it, it's just going to do a 3D placement in it. And that's it. We don't have to do anything else. So you can see that would really give us a very quick way of producing these values that we want. West, east, south, north, down, up, right? So I can get the values out of my cube lighting by doing 6 textile fetches, well, I shouldn't say textile fetches, 6 texture lookups that will themselves do the trilinear filter, right, to filter the map. And then, once we have those values, we just need to combine them into a lighting solution. So we need now some way of saying, okay, let's light the pixel based on now what we know, right? Okay. So when we do this, when you can see here where we do this SomeLight call, well, the problem that we have is when we're summing the lighting, we now need to be able to do the lighting equation based on light that's incoming from different directions, right? We have a west, east, north, south, down, up, etc. And so we need to be able to say, well, like, give us some indication of if light were coming from there, how much of that light would be reflected back out at us, right? How much of that light would be reflected back towards the direction of the eye, first of all, and then, related to the surface normal that we are given. And so this is just going to be a straight up lighting equation here, and I want to put that in. But at the moment, what I'd rather do is actually say, let's hold off on that for a minute, because if I were to put a complete lighting equation in here, then we also have the problem of, did I write it correctly, right? Did I screw up the lighting equation? And so when we look at what comes out of it, I could have made any kind of error there. So what I think we want to do first is let's just test each individual lighting channel and make sure that we can actually sample them accurately using this technique to make sure we don't have bugs elsewhere in the pipeline. And then once I know that I'm actually sampling each of these lights properly, then we move to computing the lighting equation with some confidence that we have done the underlying work properly, so we're only debugging the lighting equation itself, not the inputs and the lighting equation, and having no idea what we've screwed up, right? So that's what I'd like to do first. So there's going to be a to-do here that's like insert lighting equation here. But what we're going to do first is when we return lighting information from the SomeLight, we are just going to return the lighting value from one of these things, let's say. That's what we're going to return. And so we are going to have a light data that's going to be in RGB. What I'm going to say right now is we're going to take light west.rgb and multiply it by light west A. The A value, I'm going to say, that alpha value, we're going to encode the intensity of the light into that. So that way we have an RGB, which gives us 256 levels of precision on each color gun, and then another value which basically scales them. This is just a crappy way of doing an HDR encoding, basically. And so what I want to do is say, all right, we'll take the light here. That, if I just did it by itself, would allow us to get from 0 to 1 brightness in R, G, and B. I want to be able to have a broader range. So what I'm going to do is say max light intensity, right, times that A value. That allows me to take the alpha value and say, how bright is this light that's incoming here relative to the maximum intensity of a light in general that we can possibly have in the game? What's the brightest light? And then the RGB is just a way of colorizing that light. So we have a way of having a broad, like basically an exponent on the light. And, we may want to change how this is encoded. I'm not saying this is exactly how we want to encode it or anything. But, we're going to start with that. And then as we go, we may change it around, right? And so then up in here, for the moment, because I don't really care, I'm just going to go ahead and quickly define this to max light intensity. That's going to be a floating point value that just gets input into the shaders So here I will have a max light intensity value. That's probably just going to be something that we define in the render itself. So in the Handmade renderer code, where we're starting to define things here, like the light data width, that sort of thing, we're just going to say that there's a max light intensity, and that max light intensity is whatever it is. I don't know what it is. Maybe it's 10. Who knows? Not my problem right now. That will be something when we go to tune the actual lighting, figure out how bright we want our brightest light to be. Don't have an opinion. We don't even have exposure control in this game, so, you know, that's for a later day. All right. So once we have that piece of information, we now have the ability to call the SomeLight function, and the SomeLight function returns the information that we actually needed, which is how bright the lighting should be on this thing, right? What's the inbound RGB light? And eventually, we're going to have some real information there, but for right now, all we're going to do is say, what did the west field say the lighting was, and we're just going to return that. Don't care what the normal is, don't care about anything other than the position of the pixel and what is in the west side voxel at that point. That's it, right? Okay, so assuming that we wanted to do that, what I'd like to do here is maybe get rid of this if lighting disabled thing. This SomeLight can just sit here now. And if the lighting is disabled, it simply won't call it, right? So the fact that SomeLight exists there and it multiplies reflectance, that just won't happen if lighting is disabled, right? So now what I'd like to do is make lighting not be disabled. And so when we compile the ZBias program, you can see it down here where we call this. You can see that there's like a setting for lighting disabled. If we search for that, let's see where that is. Here is our actual disable for it. There we go. And so if I just say no, we're actually going to do lighting now, as scary as that may seem, we should be off to the races. And we will start getting compile errors on our shaders, because we probably screwed those up. Once the compile errors stop, we will be totally borked because it'll just be, the color will just be black, presumably because we haven't even sent down those samplers. They're gone, right? So now we're just going to start the process of feeding something into these voxels and seeing if it works, right? So that's where we're going now. Okay, I'm going to open up Remedy, the debugger of choice among Handmade zealots such as myself. We are going to run the game, and in theory, if we don't, well, and we didn't even crash. Oh no, we did. I'm assuming that we, well, crash is the wrong word. I'm assuming that we will fail the shader validation, and we did. So first things first, let's make our shaders actually work, and then we'll have the problem that they're sampling no actual light. Oops, fragment. So here's what it reports back. It says error, undefined variable, surface reflect. Let's go see what's going on there. So if I jump to the ZBias program and I look at it, surface reflect isn't used until down below, right? So that's actually here. And, excuse me. It looks like the problem we have is that it's only if the mod color A is above the threshold does it actually do this operation, right? I think that's because this, and that's probably right, but I think this brace here was like an errant brace. I think that looks like the actual problem, right? And so if we just delete that brace, this was getting wrapped into its own little clause here, but this whole clause wants to actually be that. So I think that was all that particular error was. Let's go back and, excuse me, run this again. And we're running in debug mode right now, so it's a pretty slow startup, unfortunately. So there we go. And I think, you know, I don't really know, but I think this is sort of what we would expect. Like I said, everything would probably be black. And the reason for that, you know, and even all this stuff is still going through that shader, and we're going to have to make sure that we do a lighting disabled call for those, I think. Some way of disabling that lighting. Because otherwise we can't even access our UI, right? But that lighting that's in operation right now, what's happening is, or what I believe is happening, right, is that we're now sampling lighting, which will affect what we're doing. We're sampling that lighting from a source that's always going to return 0. And so we just get a black screen, which is exactly what we would expect. Now, I just want to verify that that's sort of what's happening, because, again, it's GPU programming, you can never be too careful. I'm just going to go ahead and assign the normal. Whatever the normal is getting passed down, I'm going to go ahead and assign the normal to the output lighting channel, just to see whether I see anything on the screen. And again, that's just me trying to ascertain to what extent this shader is working, right? And so if we look at what we're seeing here, this is roughly what we would expect. So here are our normals, and if you look at like a cube, you can see that it looks exactly like what we would expect. The faces that are facing in the positive direction, well, actually, no, you know what? There is one bug, which is I would have expected this top. Oh, you know what? It is blue. It's just, it's so dark. The top is so dark in the texture that it's getting nullified, because these are all blue. So you can see the positive direction is always bright. So if I look at it from this angle, you can see I see blue, green, and red on the 3 positive directions. And then these should all be black because they're negative normals, right? And I can fix that, obviously, if I wanted to. I could do something like this. Also, isn't F not allowed in shaders? Why didn't I get an error on this? I thought, for some reason, I thought GLSL doesn't allow you to put an F in there. Am I just imagining things? I thought like in 4 you can, and 3 you can't, or some crap like this. I don't even know. I think maybe we want that. I'm not sure, but I'm gonna do that anyway. Anyway, so I can adjust these into the visible range just to make sure, but basically, yeah, it's just, you know, something like that. And then we would get, you know, we'd bias it up so it's all in the visible color range, because negative, you know, there's no such thing as negative colors when you're outputting pixels. You can only 0 is the lowest you can be. And so here's what it would look like if we actually adjusted all the colors into the visible range. You can see these things getting colorized by their direction, and just the brightness basically says which direction they're facing, right? So there's our understanding of the color values there, and everything looks, you know, roughly correct. I'm not scrutinizing it, so I don't want to say it's 100% correct, but it looks like we're fine. So I think we are correctly at this point set up to actually get our voxel sampling working, which of course requires us to actually provide these voxels somehow in the first place. And in order to do that, what I would like to do, I think, I'm not sure, because, you know, it's a little bit tough to say. But basically what I'd like to do with this voxel is say, okay, probably want to tackle this in 2 stages. In the first stage, I will output voxels directly to the graphics card, and those voxels will be the lighting that is used. That's step 1. I want to do that because I think it's the path with the least number of calls to the GPU, ergo, it is the path with the least number of GPU screwage options in it. Then, once I am sure that that is working, and possibly when I say once I'm sure that it's working, I may mean sure to an extreme extent, meaning when we know the entire lighting pipeline is now working, then I will move from submitting the voxels myself to probably just submitting a list of lights, right? So we will, step 1 is we send down 6 128 by 128 by 128 voxels every frame ourselves. And step 2 is we just send down the light probes. And in step 2, what we'll do is we'll take that light probe list, we'll treat it as a vertex buffer as if it's going to render primitives to the graphics card, right? And we will voxelize the lighting into our voxels ourselves, right? We'll figure out some way to do that. Again, that's a much more complex operation, and so I don't want to mix that with lighting. It's just an optimization. There's nothing different, right, about that. But, you know, I don't even really know exactly, now that I think about it, I'm not sure what the most efficient way is to voxelize things on a graphics card anyway. It sounds kind of nasty in the sense that you don't really specify volumetric primitives in OpenGL. I've never really thought about this, but like if you wanted to rasterize a voxel, I mean, I've written my own voxel rasterizers before, multiple times. And, you know, what you want to do is have some function that says which voxels are included. And you typically bound that and then evaluate it as you step through the voxel. That operation, I don't even know how to provoke that operation in OpenGL if it even has it, right? Like, I don't even know how you give it a boundary region and say, please step through all of the pieces of this voxel. So for all I know, and I don't know, but for all I know, what you actually need to do is you actually need to specify the slice of the texture as a render target per... No, that wouldn't work. So I guess as I'm thinking this through, I'm like thinking to myself, I don't even know how you induce OpenGL to produce the correct output to a voxel anyway. So we're going to have to go look at that. Like, obviously there's people who do stuff like voxel cone tracing and things like this. Obviously you have to be able to do that. What I don't know is, does it require a compute shader? If it does, forget that. Like, we're not going that route. But I would have hoped that they would have added some kind of a rasterization primitive that rasterizes into 3D, because, gosh, that's just kind of an obvious thing you'd want to do. It's weird that I can't even think of someone mentioning this, but it's got to be in there. I'm kind of curious. What's the Okay, so basically the answer is you have to use an unordered access view. So you don't have to go full pixel shader, but yikes. So unordered access views are like really bad. Gosh, is that really true? That disappoints me on so many levels. I'm kind of depressed to hear that. If anyone from NVIDIA is out there listening right now, can you please email me or something and tell me why that's the case? Because an unordered access view is like a very bad primitive, right? An unordered access view is essentially it's essentially a construct that breaks the ability of the GPU to know about the pixels touched by a shader ahead of time, which makes it much less performant, I would think, in a lot of cases. And in the case of voxelization, you could just have voxelization. The front-end rasterizer knows it can do the exact same operation on voxels as it does on pixels. It's just that edge inclusion operation just uses 6 planes instead of 3 planes, right? So is it just that that was impossible? Like, was it that there's no way we're going to add 6 planes to our rasterizer? We can only have 3? Because even that doesn't sound like it makes any sense to me. But maybe it's true. I don't know. But I would love to know why that was the answer. That just seems really weird to me. Unordered access view. Very depressed right now. Yeah, I don't know. Very depressed right now. All right. So if I multiply out how big one of these voxels is at worst, 8 megabytes of throughput times 6 is 50 megabytes of GPU throughput per frame. If we wanted to send down the voxel every frame, right? So if we wanted to just say, look, here comes the voxel, bro, and we sent down the whole thing, so we never did that operation that I was just talking about because OMG requires unordered access views, which is a complete nightmare. What we would want to have to do is send down what amounts to 64K, let's just say. I'm sorry, 64 megs. We're trying to send down 64 megabytes of memory or something. Actually, maybe it's closer to 48. So if I do 1024 divided by 1024, 48 megs. Sorry, I was being bad mathy. So it's 48 megabytes of GPU throughput. If we're sending that down at 60 frames a second, that's 2 gigabytes of sustained throughput to the graphics card. It's not fantastic, right? But it's not that high. So it's not out of the question that we could just do this on the CPU side. It's possible. Whether that turns out to be the right answer in the end, I don't know, but it's possible, is all I'm saying. So, you know, I guess that's just something for us to think about as we go. So if we go and we stretch our concept of what's happening here a little bit, you can imagine going through and taking the render commands that we have here, and instead of sending down the different information that we've got here, these are not potentially ever going to be sent out then. These will just be for our own personal render or use. We would just end up being in this land here, where we have the light index voxel being sent down here, and this voxel has the data in it that we actually use for lighting. What we want to do there is say, okay, this goes away perhaps, meaning this light probe irradiance, I guess, is not really a thing maybe. Well, we probably still need that for other reasons, but so what we're going to have to do here is actually pack our color values in here and prepare 6 separate voxel data chunks and send them all down as 3D textures, right? So we would need to do something like this, where we're going to pack that RGBA lighting in there and send that down as the light index voxel each time. And again, we'll do that in a not particularly fancy way at first. So here we would basically just do like some kind of a nonsense thing where we're just like, all right, each of these we're actually going to just send over. And once we've got that in place, the OpenGL version, of course, also needs to have a 6-wide thing that it's keeping for that. I guess I'll just use the compiler to jump me right to it. Or not. Okay, so never mind. That doesn't actually tell me. So that OpenGL structure there, that keeps these guys. Where does that go? It's here. So here's that light index voxel. That's going to change. You can see we need 6 of those now. So there's our gigantic thing. I suppose actually we want to do it like that. And then we're good. So now we have a place to put this information. We just need to send it somewhere, because right now we're not actually submitting that lighting information. So we need at some point to say, okay, let's bind some textures to this thing and allow them to get fetched. So in the actual code, and we're going to need to do this in a couple different places. First, here you can see where we do our OpenGL link samplers. You can see we've got the lights at the end here. We now need to change that to be linking each of these, right? And so down here we've got effectively that same list. We need to link east, west, south, north, down, and up as our set. Once of those samplers are all linked up, we have to submit them. So when we go to set the Z-bias program, anytime that's actually happening, we have to set up the shaders for it. So when we look at the places where that's actually being done. Oh, I guess we don't do it that way. Never mind. So I'm just going to jump down then to where we actually do the Z-bias program. So when we're actually dispatching primitives here in the actual renderer loop itself, right? When we're dispatching these primitives, when we get down to textured quads, then this is the place where we're actually using the Z-bias program, right? You can see it here. We start setting up our textures. You can see us setting up our textures for like the depth handle, and then you can see us sending down the light data here. This is where we need to actually specify the information that we have from the game proper. So we'd actually be switching to a GL texture 3D at that point, and we'd be setting these up as textures 2, 3, 4, 5, etc. Right? So I'm just going to make this a loop because, you know, why not? So in here, I'm going to say, well, OpenGL has some amount of light data. There's the voxel index. The voxel index will loop over to the 6 ones we have. I could do it like this even. And then it's just going to send down, if light index 2 is the first one, it's just going to do light index 2, texture index 2 plus which voxel we're trying to send down. It'll send each one of those down. Well, it won't send them down. It will bind each one of those and get it ready to go. And then when we come back here, we will turn off those textures, right? You can see that happening here. And so when we go to actually bind the other textures, we would want here to probably unbind those, although I don't know that we really care about unbinding them. They can just be left bound because no other people use them really. So I'm not sure what we want to do there, but I guess we'll just leave it like this. We send down the lighting textures here, so we don't send them down. We bind them here. We need to send them down somewhere, right? So at some point, someone needs to actually like describe these textures to the graphics card. And so somewhere up here where we're sending down like our bind buffers, you can see that happening here, right? Where we're sending down our bind buffers, we need to actually submit all of the data. It does strike me as odd that we do the buffer data submission before we change the settings. Seems like you would really want to do that after, but I guess I don't know. We'll leave it there for now. So what we need to do here is actually submit these textures. So here we need to effectively do a GL texture 3D call, right? And I think we want a text subimage 3D in this case, because we're not changing the format of the texture. We're not changing the dimensions. We're not doing really anything to it. All we're trying to do is specify a new set of data for each one of those handles. And so what I'd rather do here is just like resubmit, right? Just resubmit the data that we've got. So if we were to look at the GL text subimage call, here's an example of that call. We're going to be doing exactly the same thing here. Only we're going to be specifying an entire texture rather than a slice. So if I go in here and say, all right, we've got GL texture 3D is where we're submitting this thing. We've set our GL active texture to this thing. We then have a MIP level of 0. It will always be 0. We're in the upper corner, which is 0, 0, 0. We then have a width and a height. We know what those are because we've sort of pre-specified the dimension of our lighting voxel. It's actually up here. Where is it? Here, right? So we know that we're always sending down something that looks like that, right? Because it's just, we're never going to be doing anything different. I don't know if actually we should be, well, I don't know. We're going to leave that like that for now. Let's just do that. So we have our voxel sent down as a complete 3D texture. Let me go back to our text image 3D call. Here we go. And then we just need to know what the format is. So we don't really need BGRA-Xed probably, although we could send them, since everything else is BGRA, we might as well stick with the format so it's not like, oh, just the lighting is the wrong way around, I guess. We're going to send it down as an unsigned byte, and we're going to send it down as this voxel information here, right? So now all we're doing is at the head end, we're sending down all that data, then we're binding it later. Looking here, it looks like the light data is the wrong thing to say there because that's probably not what we called it. If we look at the OpenGL struct like I did before, you can see it's not that. Here it is, right? So I guess we kind of want to call that the light data array, maybe. Seems to be what we're calling it elsewhere. So we'll just do that for now, and we'll worry about the name of that later once we actually decide on this technique and make sure everything actually is working for us, because we might change it up, and so we need to know what's going on there. Don't ask me what this was supposed to be. I have no idea what was going on there. That's just my brain being, it's a brain fart, just a straight up brain fart. Obviously we need texture handles for this light data, so I'm not sure what I was thinking. It's this that we actually need. So we need 6 of these. These are where we would specify the textures initially. So these are just handles. It's like this is the OpenGL handle we're going to use to talk about this texture. And that's what actually needs to get bound and submitted, right? So that was just brain fart. Here we need to do that. So we need to specify that here. We say for this texture, we're going to bind and go. This was the wrong thing to think about. We don't need that, right? We just need this. Right, so when we do GL bind texture, GL texture 2D, right, then we come in here, we're going to unbind it. You know what I'm saying? So we do a bind, then we do an unbind just to clear that out. So I think that's what the flow should have looked like. I don't know why I did it the other way before. I just did. So now if we look at GL text image 3D, you can see that getting specified here and here, right? And really what I want to do is I want to do the same thing I was doing in this call. I want to generate these textures for our light data. So in here, I want to do a thing where I say, all right, let's loop over the Vox index here, just like we were doing before. I want to generate texture handles of that order as well. So light data handle and array count. So generate this many handles for us. Each time through here, I want to do exactly this. I want to grab out the light data. I want to bind it. And then I want to specify some stuff, right? So first of all, we're not going to do any nipping on these things. We are going to be specifying the standard format that we have been, which I think is GLRGBA8, right? We want the width, height, and depth. Width, height, and depth. It's hard to get those straight. And that's our light lookup voxel dim. Like so. We then need to specify how many nip levels we want. Is that what that is? I don't remember what that is. Then we want to specify the storage format, which is what that is, and that. And then we're not going to provide anything. So we're just telling it, look, this is how much space we need. Be ready, right? So that's the long and short of it. I'm sure we've made plenty of bugs in there because GPU code is always riddled with bugs. But that's basically what we're doing. Create the handles, tell OpenGL how big they are, every frame, send down new data, and then bind during ZBias program. That's what we need to do for the most part. And looks like we got, oh yes. So when we're deleting these textures here with the light data, I'm not sure. So are we actually creating them in here though? We are not. So this stuff needs to go because that's not actually happening anymore. And those I don't think get deleted in here. Those are just permanent, right? Yeah, because I don't think we need to do that. So that's all fine. So all I'm going to do now is just go and see about setting up the filtering on this thing. That's the only thing that we haven't done. So if we go look at our light data handle, where we create this thing, this part here, where we set the texture information. So I don't really know what we want to set here. When we do min and mag, we're doing linear sampling. I don't know to what extent that applies in 3D, but I assume it will. And I assume we can also do, when we do texture wrap, I assume we can clamp the U as well, but don't quote me on that, right? So I'll have to look that up. Let me see what else we got here. So render entry lighting transfer, pretty much not going to allow. I don't think at the moment. So I'm going to get rid of that. And I'm also going to just assume that no one can send that down. So if I look at the renderer, I'm going to get rid of the lighting transfer. So that's just not allowed anymore. And anyone who was using anything like that should go away. Yeah. So let me take a look at what this is supposed to be. I don't know what those are called. I'm going to go to docs.gl. I'm going to search to see text param. Just to see what's going on in there. If I look at the settings, you can see here's the wrap. So there's wrap S, there's wrap T. I don't know what wrap R is, but maybe that's the thing we want, STR. Say. So that must be it because it's the third parameter, right? Let's say it is. I have no idea. So we're probably going to have to define GL texture wrap R ourselves, right? Because that's probably an extension that was just for 3D textures, so it wasn't in OpenGL 1. So if we go look at like, you know, GL Core or what was the thing, glx.h or whatever. So if we look at like wrap R, you can see it's just this thing. And that should be all we actually need. So not a big deal, right? Probably we should have grabbed it in here. Just wasn't thinking about having to do that. In fact, maybe the best place to put it would be down here, because that's where it would really be used. So I think that's everything. So now in theory we're sending those down, but again that's really just only a theory. I don't actually know what's going to happen here, and we may also have bugs. So the first thing we're going to want to do now is go into the code and try to provide like some kind of a that's interesting. You can see like little seams. I wonder what those are coming from. Are they fog maybe? Anyway, we're going to want to go into the code and try to stuff one of those voxels with an actual color so we can see that it's getting selected, right? And so the easiest way for me to do that would be when we go to finish off our lighting. So in like lighting test, for example, or I guess it's not lighting test anymore. It's called like end lighting computation. Yeah. So in end lighting computation, in here, what we would do is when we get down to the end, right, we would basically say, all right, we now want to write to this voxel. So let's just write something to it, and it won't be correct at all, but we'll just write something to it. So that, excuse me, that command buffer, which is in here. So here is our command buffer. We have these light index voxels here, so we're going to want to do like game render commands. Commands equals render group. Might just be group. What is it called in this function? Group. So we might want to just say like, okay, group commands. Now we've got it. Commands light index voxel 0 or box surface west or whatever it was. Box index west. So what we believe to be the westward facing voxel, like so. I want to go through and I want to write to that thing. And I could do this actually by being a little bit more expansive. So maybe we'll actually do it a little bit differently, but point being, maybe we'll do this. I'm going to have like an X lookup here. What was this called again? Oh, you know what? It's actually right here. So if we look at the light index voxel dim, we know exactly what we're talking about here. So if we step through this like so, we know that now we should be able to produce this piece of information. There you go. So in theory, this would loop over the entire voxel. And then what we could do is we can write something in there to one of the channels, whatever channel we want. So maybe we do something like this. Light index voxel, box index west, and then we further address it as z times cz plus, well, actually, I guess we can do this as sort of a stack. Maybe. I don't know how I want to do this exactly. That's a good question. Well, I guess we would do it like this. So I guess I'll just write it like that. So we'll just write it out longhand. That's the address of this particular cell in the voxel. And then I'm just going to assign it some color value. So I'm going to assign it a color value, let's say, of maybe something that looks like that. So that would be red with a, medium brightness red, I guess. Okay. And now we can do, we'll take a look at what this outputs, but now what we can do is we can actually go and start using RenderDoc or, something else. Well, all right, so that just worked, right? So now we know we're stuffing that voxel. And what I'm interested now in figuring out is when we're looking up this voxel, to what extent is it actually spatially querying? So what I want to do is I want to then say, all right, let's suppose that we wanted to introduce some kind of an X striping. So I want to go ahead and say, look, let's say X mod 2. So every other cell, I want to do a different color. So I'm going to actually do something like this, where we do red, blue along X stripes, right? Insufficient disk space. Yeah, right. How about you already had the file locked? Anyway, so now I want to write that out to the lighting buffer and see if I see anything, right? I should now see different colors coming through, and we'll see what happens. But I don't, right? So this is pretty important because this means like something's busted. You know what I'm saying? As this steps through, I should be doing like this or this on alternating indexes of the voxel, as far as I can tell anyway, right? So I shouldn't have only seen that one. I should have seen an alternate of each of these. And the question is why? Well, the first thing that comes to mind is I think we forgot to ever actually send down the constants. So probably it's looking into only one cell of the voxel. What do I mean? Well, remember I said in order to map this thing into the voxel, we need to actually set up the voxel, right? And so I defined these two things, voxel min corner and voxel inf total dim, but we never actually specified what they were. So in here, where the camera information and stuff is getting sent down along with everything else, those need to be there. So we need to sort of query these two constants that are going to come down, and then we need to actually say what they are once we get there. So in here, we need like voxel min corner to be equal to something, and we need vox inf total dim to be equal to something, and we need a way of specifying what these are. So in here, we would say voxel min corner, voxel inf total dim, and then in the actual definition of the z-bias program, which is this thing right here, we need to remember where those are. So here are those two things. Oops, that's not what I wanted. And once we have those, now we can actually specify them. We need some way of actually getting them, which, has to happen as part of the render pipeline. But once we know what they are, the rest of it's pretty simple. Because you can see here when we go to do the z-bias program, we already had to do a bunch of this stuff. Anyway, we have to send down those constants. And so that's actually something we needed to do.
when we specify these constants, is anyone's guess? I don't remember where we specify the constants, just to be clear. Looks like here. So when we specify the constants here, you can see us grabbing the stuff out of the prog, like where we asked for that stuff before. And so we need to, get this information from somewhere, right? And it's going to have to come down as part of the use program begin, I believe. Like that. So in order to make this work, this will have to actually get that information from somewhere. The alpha threshold that's getting sent down, I don't know where that actually comes from. Looks like it's just determining whether it's peeling or not, right? And so what we really want to do here is say, well, the actual drawing primitive itself, this render setup, probably is the thing that has to have that. Because it's going to have to be specified by the game. We don't know where it wants the lighting applied. We have no idea. So we kind of just have to trust that it will tell us how big it wants the lighting sampling to be at any given time, right? So we're going to have to send down the voxel min corner and the voxel imp total dim. That's going to have to be like something that just gets told to us by the game. And the render setup in here, for voxel lookups, it's going to have to set up what those are, right? So we need to look and see, like, where is the game setting up this sort of stuff? Where is it actually specifying this information? You can see in here when the game does this, like under set camera transform, it puts a bunch of this stuff in there. What we're going to need to do is something that actually like modifies that piece of information, I think, to a certain extent. We're going to have to like write that up. So in there where you see that push setup call, right? You can see it doing this nonsense here. When we're doing that push setup call, you can see it writing it to last setup, right? And I want to say that, yeah, like probably we just have to fatten this up. Which I don't love. I don't love how fat this has become. Don't get me wrong. And we probably should fix it. But at the moment, we're not going to, because that's not what we're doing right now. But someday. All right. So in here, I just got to set these. I shouldn't have done one. It's not a floating point constant. It's actually a vector constant. So that should be fine. This right here is just specifying one of each of these. I guess, why did I pass that? I don't know why I passed that. These are actually in the setup. That was just dumb. That looks like that. Cannot convert array 3 to GL float. Right. Sorry about that. There we go. And then this doesn't have to actually send that. There we go. So I think that's all good. No worries. And so now I believe we have the ability to specify this information. If I run the game again as it is, I really shouldn't see anything different because they're still getting set to 0, since even though we're specifying them now, nobody's actually passing anything to that setup routine. So I think it's probably just going to be exactly the same as it was, and there really isn't going to be anything special going on there. So I think that's all just nonsense and doesn't matter. But if I actually go now specify that part
stuff as part of the camera transform, which is here. I'm guessing that if I start to pass something down for, I guess not the debug camera, but for the regular camera here, if I go to well, I guess I'd probably want them for both, honestly. But if I go ahead and specify what the voxel dimension is at that point, I should be able to make this now start to bound the region. During that set camera transform, we need to know where the lighting voxel is. That creates a little bit of an issue, right? Because that set camera transform is sort of happening before anyone has actually figured out where the lighting bounds are. And if you look at the world camera rect, well, the world camera rect happens like here. And so we have kind of a nasty like pre-computation problem where we're like, crap. We're asking this thing that, like, we need to set the voxel information after we've already finished. We rely on the camera setting call to tell us where the lighting should be in the first place, is the problem, right? And so we do need that to be fixed, and I'm not sure exactly how to fix that. But I guess that means we will have to fix the thing I was saying we don't want to fix it right now because we're doing something else. I guess now we're doing that because this is exactly the problem, right? What we want to be able to do is right here when we do begin lighting computation, we want that to pretty much use the light bounds to set up the render target, right? So we want to do like set light bounds on the current render setting. And we'd pass those two things down. Whatever the min was, so it would basically be like light bounds min. And then we would take whatever this dimension was. And then we'd want to do like something that inverts that. So then we would do something like that. I don't know if we've got that. So that's what we would like to do. We'd like to be able to call set light bounds and have that just work. And then we would like that call that I made there that was like the render group call on set camera transform. I don't really want that, right? What I want is something here that sets up the light bounds separately. So you'd pass in just these two when you want to, and that would sort of like do it as a separate part of the process. So in here, do we ever actually push this on somewhere? No. In here, we want to basically like change what the setup is for people who are currently using that setup. You can see in here, you know, people do that push setup call, and I guess I don't know exactly how they get that information back out. I haven't really, you know, I don't recall how we meant for that to work. But like, you know, here's the setup that's actually being used in group last setup, right? I'm assuming that it's okay to just call set light bounds at that point. What happens during get current quads? Does the setup get recorded at that point? Yes. So I think it's really pretty easy now that I think about it. I guess all you really do is this. I think that's it. So now in theory we have the ability to set the lighting bounds to something, and now we just have to debug that process. It looks like we got lucky. That's exactly what I wanted to see happen first with the lighting. And so you can kind of see like somehow this went well for us. And, you know, yeah, I mean, that's rare. That's not how GPU programming usually works. So that went way better than I expected. If we're now gonna try and verify that the lighting is interpolating properly across all of our various dimensions, the other thing I would do is I'd take that west when we're specifying that voxel in the end lighting, so end lighting computation here. If I was to go ahead and stripe all 3 dimensions, so let's say we go down here and we look at where is that? There it is. If I was to sort of build this up as a progressive value, so this is the light info, and I say like, okay, it's that, you know. If I wanted to build it up incrementally, what I could do is say, you know, if x mod 2 light info or equals something, right? Y mod 2, Z mod 2, and then here we just say like light info or something, right? And so then what I can do is say, all right, let's stripe, you know, each of these. We'll say that the red stripe, green stripe, and blue stripe corresponds to stripes in X, Y, and Z. So we now should see like those stripes intersecting each other and providing like an actual different Z, X, and Y striping layer, right? And so if we actually look now at what we get, and we can ask ourselves the question, does this actually make any sense, what we're seeing? So if you look on here, you can see that effectively what it looks like we have anyway, is you can see like a red stripe. Well, actually, what does it look like you can see? I did those backwards. That's blue. This is BGRA. Sorry. Forgot we're BGRA everywhere. I'm RGBA everywhere on my code base, so yeah. All right. Try that again. So now it's a little more sensical because it's what I said instead of what I typed. So you can see the red stripes going in X. You can see the green stripes going in Y. And the only question is, can we see any blue stripes, right? And so if I look from the side here, what you can see is there are some blue stripes, but I'll be honest, they don't really seem to make good sense to me, right? Like I don't... like the green and red stripes seem pretty clear, but if I look from the side here and I look at the blue stripes, oh, well that there it looks right. The blue stripes do seem to be stacked, which is what I would expect. They just don't seem to look like it here, but I guess that's because I was misinterpreting it. It does kind of look like it now that I look at it. Okay. So I think our lighting is pretty good now in terms of the lookups. Like that's looking up correctly, as far as I can tell. And the only thing that's a little strange is the region that is getting lit. That's a little bit strange to me. And the reason that it's a little bit strange is if I just look at the region, it looks to me like the region is here, which, well, maybe that's correct. I don't know. It's hard to say. I would like to maybe go a little further. I'm going to go ahead and, you know what I want to do? I'm going to go ahead and go into release mode here. So here's me hopping along, and you can see that the lighting volume is kind of moving through the space. We're going to want to not have it do that, by the way. We're going to want to move it in fixed unit, fixed voxel units so that we don't see any popping. But that's kind of a separate issue. Anyway, I'm going to go down here to some place that has a little more depth to it, right? So I can pull back and just see what that actual region looks like. So, I mean, it looks all right, you know? So I think we're getting, I think we're in usable territory now, right? We can work with this, right? And so I think that's a great place to end for today. That's where we want to be. We're doing our voxel lookups now. And I don't know to what extent our speed has been impacted. That's a little bit tougher to say. What I might want to do here is say, all right, let's see what Insight says for our speed. So I'm just going to launch Insight real quick. That looks fine. And I'm going to go ahead and just launch the frame profiler here. See what it says. So if you look at the actual speed it's reporting there, it's 43 frames per second. That's like significantly worse than we had before, right? We were like way faster than that previously. And so I don't know what to make of that, but if, you know, I'm scared. I'm a little bit scared of what that entails if we really are getting that slow of a frame rate, because I don't know what's causing it necessarily. We could look. In fact, let's take a quick look. And so looking now at what we're seeing here, you can see this draw call here is taking quite a bit of the time there. Although, you know, honestly, looking at this, I'm not sure I understand what I'm actually seeing, because I guess this would imply that we're CPU bound, though, maybe? Because just looking at it, doesn't look like it thinks we're taking anywhere near what would it be, like 30 milliseconds? No, 28 milliseconds. It's not reporting anything close to that, right? So this number is drastically higher. And so I don't know if that just means we're totally CPU bound at this point, which maybe we are. And that's totally great, because if that's true, you know, obviously we can try and fix that. Let me real quick just play with one thing and see if that's true. So if we go in here and say, you don't need to do this anymore, how bad is it? Doesn't look like it really changed much. So I'm not really sure. We're going to have to do some inspection. We have to like re-enable our profiling as well and stuff like that. So we'll see. But that'll be our work for tomorrow. I'm totally fine with where we're at right now. Let me go ahead and terminate here. And we can start to look at that later. All right, let's go to a brief Q&A. Anyone have any questions on that? All right, so I guess no questions, sounds like. If there's no questions, we can wrap it up, which seems good. All right, there does not appear to be any questions, so I think I will go ahead and wrap it up. Oh, no, there was one. In the pre-stream, we were talking about creating command buffers in your theoretical graphics API. Would this be like a buffer you would dynamically assemble GPU machine code into, or is it something that the driver would need to translate for you to the GPU machine code? So my opinion on that is it should be... The answer is yes. My opinion on that is what should have happened with, for example, Vulkan, is rather than making it all be ridiculous crap we have to call the driver, what should have happened was they should have specified a specific format for everything. So every possible command you can send down to the GPU is spec'd as a data spec. You then, all of your first wave drivers have a translator in them that translate from the software spec that was specified to whatever the hardware actually ingests, right? Then the next round of GPUs they all just make the silicon read that directly. And then that entire part of the driver is gone for the rest of time, right? That's what I think should have happened. Isn't SPIRV the thing you're talking about? No, SPIRV is not only not related to command buffers, it's for shaders, not command buffers. But it also doesn't do that. SPIRV is not designed to be something that hardware actually interprets itself. SPIRV is designed to be input to a driver compiler that then compiles output code, machine code for the chip. It's not designed to be something that a graphics chip would ever actually execute directly. You can think of it, in fact, it's right in the name. SPIRV, the IR is intermediate representation. It is not designed to be an actual executable format. It's designed to be basically the first step of the compiler, which parses and turns into an abstract syntax tree, then possibly static single assignment forms the data, the code. Then before you actually generate any machine code out of it, that's what SPIRV is. So no hardware would ever take SPIRV. The only reason hardware would ever take SPIRV is if you chose to then actually have a small core in your graphics card that was like sitting around running a compiler, which you could do, right? It's not the world's worst idea, but you know that's the only way that a graphics card would ever run that natively. It's not machine code. It doesn't look like machine code. Fable Protector, unrelated question. How would a highlight shader work? If you want to select a sprite, you'd want to color the edges of a sprite in some color. Is this done via the stencil buffer? So I guess I don't know how I would implement that. I've never actually implemented that specific thing you're talking about in that way. So my first thought would be something along the lines of
inside the pixel shader, maybe I would just do a thing where I sample from the... So, completely off the top of my head and probably stupid, is I would say, what is the thickness of the outline that I want? I would sample from the MIP map that is that thickness, that corresponds to that thickness. So if it was like 4 pixels wide, I would sample from the MIP map that was 2 steps down. And I'd say, what is the alpha value? And whatever the alpha value is, I would take it, and if it was 0, I would discard, but if it was non-zero, I would draw the outline. That's a really bad answer, but that's the first thing I thought of. I mean, basically what my thought process was is, can we do a signed distance field here? And the problem with a signed distance field is that you either have one or you don't. And so with sprites that are actually just stored regularly in the texture, you don't actually have a signed distance field. So you can't just say how far am I away from the edge of the sprite. It doesn't tell you that information, right? But you can approximate that information by just fetching a sum of the area and seeing how close you are to actual pixels, right? And so I don't know if what I just said would work, but it was the first thing I thought of to approximate a signed distance field. Brian asked what happened to the profile. Just before the stream, you mentioned you want to re-enable it. Was it disabled or not just tracking? The reason that the profiler is not visible is because we turned on lighting. And so what happens with lighting is everything is going through that lighting. So we don't currently have a way to turn the lighting off when we go to draw our profiler. So the profiler is still there. It's just getting lit by black. That's all that's happening. All right. No further questions? All right. Thank you, Brian. We will have fun gaming with John, I'm sure. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can play around with it yourself. We've got the basics of the lighting system in now. Maybe today would be a good day to play with it yourself. See if you can get some lighting working before I get to it tomorrow. Everything's set up for you to do it, right? So that might be something to try. That's about it for today. I will be back here tomorrow to do that extra lighting work. But in the meantime, you may want to stay tuned to the Handmade Hero channel, because we're going to be hooking up with Jonathan Blow in a couple minutes here to do some multiplayer gaming. Those of you who joined us for our Satisfactory stream know that we are definitely pro-level gaming streamers, obviously. Don't let the fact that I don't have a gigantic chair with a headrest fool you. Obviously, I am still poning noobs with 2 zeros, as they say, all the time. And so we're going to be getting to that at about 2:30, I think. So about 20 minutes, we'll be making that happen. So stick around for that. I'll shut down the stream and restart it so you'll get an actual notification when we go live. But we'll be doing that at 2:30. It'll be on Handmade Hero channel, and it should be also on Naysayer88 channel. We'll squad up for that, so you should be able to switch between them cleanly. And we'll see you in a few minutes.
That's about it. I will catch you all in about 20 minutes. Take it easy, everybody.